So keeping the vision, computation jockey. My name's Daniel Rockets Reynolds from Buffalo Public Schools. How it's going to start is I'm going to talk for about, I'll watch the time, I'll talk for about 10 minutes and do a demo for about a minute, and then Tom will talk for 10 minutes. Keeping the vision is kind of standing on the shoulders of giants is kind of a thing people say a lot. Stephen Wolfram and treating data, you can treat a lot of different types of, through functional programming, a lot of different types of math is equivalent. That's something we're very trying to make use of. And also people like, these are just a bunch of the books that I use, Computer Simulation, Modeling Nature, Mathematica Guidebook. This guy, Michael Trott, in his book on Graphica and all that. This book by Tom Wickham Jones was a big influence. It's about a 20-year-old book, but you see it's a pretty trippy, colorful color. And it made me think, we can get kids enthused. Eric Weisstein and his work on cataloging mathematics, and all these people are the people who influence me, and I want to share that, and that's keeping the vision. It's a play on words, the vision of those people, but also visualization in general. That's the theme. Okay. Straight out of computation. So imagine CJ being able to DJ any form of data as a form of expression for the modern age, like mathematical landscapes, or you could even put fish populations if you're playing the fish market or something as a DJ. You could, Stephen Wolfram talks a lot about alien artifacts, and we were saying it looks like an alien artifact because it's so cumbersome, but hip-hop culture has been around for over 40 years, and it's a way to try and get youth, broken glass everywhere, people pissing on the sidewalk like they just don't care from Grandmaster Flash. That's a situation a lot of students I work with live in. I work with mostly immigrant and refugee students in the inner city, as well as predominantly African American population and a lot of low income students. And we just want to find a way to get, this stuff, computation into people's heads. And a lot of people see things in their heads, people in the city and kids and things, and it's a good way to give them creative ways instead of getting in trouble all the time teaching about computation. Visualization influences on me. Here's Toccata and Fugue from Walt Disney is a visualization. Here's a guy, John Whitney, his experiments in the 60s. You can see him on a computer doing visualization. We got Jefferson Airplane from 1969 with a liquid light show, and a lot of artists that influenced me that use geometric stuff, Vasily Kandinsky, Juan Miro, and we got Man Ray. And then here, I was a big influence. Bill Thurston's a big influence to me. Here's the not hyperbolic geometry. Escher got me into hyperbolic geometry, and I continued with Thurston. So we can continue. This is some of my own drawings of the type of manifolds I've always kind of seen in my head and stuff when I close my eyes and stuff like that. I've always sort of seen objects and shapes and things. So I've got like hundreds of little drawings like this that I do, just on ideas. And I want to DJ landscapes like this. And kids could do that too, as well as other types of math. So I can continue. Here's some things I'm interested in. Like we see z to the second plus c for the Mandelbrot. And here we've got Mandelbrot z to the third plus c. But if you put in z to the 2.5 plus c, you get something that's transitioning kind of smoothly. I might not use the term right, but so let's take the z to 2.5 plus c, and here's z to the 2.5 plus c to the second, because this is c to the 1, because the exponent is unexpressed here. And then here's z to the 2.5 plus c to the 2.5. You can see. And sometimes I'll just type in like z to the 5 over pi or something, I'll get all different types of ways to extend a Mandelbrot. And I'd like to, do things in Mathematica we're still working on, but being able to move to like all like tons of dimensions, off like pressing buttons on controllers and adding things to the Mandelbrot to move and turning knobs and go around the landscapes. Types of devices. Today we're going to show you Chaos Pad and Chaosilator. That's an XY grid. Then we have SO for a turntable unit. We're trying to do a lot of Fourier transform to send it and wavelet stuff, but we don't have it interacting with Mathematica yet. But what we do have is a Chaosilator, but I'm going to do something with Stephen Wolfram on there. And we use APC 40 control board. We don't have with us the SCB 1010 foot controller just because we're trying to keep it simple. It would take a little bit longer to set up if we brought everything. We're also trying to put EEG sensors, so if we're DJing all the data, our brains could be tripping out and sending like signals too, and just we could be trying to control it even. body sensors. We could get our heart going, and that could be pulsing in visualizations. Instruments and microphones. If we had a whole band, a drummer, and everything's moving around on the screen. Microscopes. You know, and with all the new image processing stuff in 11, it's really with Mathematica 11 that these dreams are probably going to become more into fruition, just because there's so much more with signal processing, liquid light shows, and video mixers and stuff. We'd really like to do things for parties at like gravitational wave detectors like LIGO. I wrote to, you know, I wrote to Indigo one time in India and asked if I could go DJ some of their stuff. ELISA, which is coming up, and Bicep 2, all these gravitational wave detectors. Particle colliders like LHC, they might build a super collider in Beijing. I read a lot of their particle flow algorithm pre-documents and stuff. Slack and Rick and the older stuff. Neutrino detectors like Super Kamiokande and all that. You know, sky surveys, you could get stuff from, you know, you could put WMAP and Planck isn't up there, but you could also get Kepler, and maybe we could take the, like all of the analysis that you're doing of the stellar objects and load them as objects. Like you could load up the Horsehead Nebula or something and get like streaming data of it and in your DJ simulations. You could do gravitational waves. They have the sound. If you like when they made the recent detection, you could load it as a sample like while you're like scratching. That'd be a good idea, I think. And then education, we're trying to build something where you can do your whole content with DJ controls. Like if you have a PDF, you could just press a button, and then you could use a turntable, shoot a turntable ahead, it would move the PDF page forward or pull it backwards, or if you want to load a document or a physical simulation. If you had like the Boltzmann equation, you want to make it something go backwards, just spin around and all this. And if you had color cycling on a fractal, you could do the turntable backspin and the color cycling would reverse. And a bunch. That's some of the things we're working on right now. We're just going to give you a little demo. Is there anything else? Any more slides on this part? So that was the end of the part I'm going to talk about. And then we're just going to do a little demo for about a minute, and then Tom will talk about how he worked with me to engineer some of this. So we're going to we have to switch something for a second. Okay, there we go. So that's Tom's monitor. I'm using a little mixer thing here. And we got a talk box over here. When Tom brings his second window over, which he's got up on the screen, he's bringing it over now. And like we said, this is a XY grid. Usually it's centered because we're not used to this screen. But if you can see this on this grid, we can move the function on here. And actually, if I turn this up, actually going through. One, two, 1, 2. So as you can return low. And when we press the buttons up here, we can get different ones that we've programmed. It's not looking centered like we want it to, but see. Yeah, I can overlay it. So over here, we've also got we got some videos of somebody who's kind of famous. CAs. Here, turn it down for a second then. Okay. So he's got CAs loaded up there, and over here, let's see. We've got Conrad Wolfram, and
nice stuff to happen in quite small programs now produce really nice, colorful. Raw dope in this case is program code. Raw dope of that. The raw dope is program code.
50 cent. Okay, and so that was an example of and we have pretty good
50 cent. He's talking about 50 cent.
Kind of an amusing example where absolute horror. Computations that involved money. Suddenly we're going rapping and so on. So there are these things that are going rapping and so going absolute horror, 50 cent. Okay? And so that was an example of, and we have pretty good systems for picking these.
So he said 50 cent.
Example of where, absolute horror, computations that involved, money. Suddenly we're going rapping.
1 second.
So there are these things where you have to be careful as you knit new knowledge in, and that's
So
something.
he's talking about you heard him talk about 50 Cent for a second. Let me just put this in. Is anybody here? Let's see, something got unplugged. 1 second. Tom, would you like to talk for a second while I plug this in?
Oh, sure. Yeah, my name is Thomas Carpenter. I work with Daniel Reynolds. I'm a software engineer, a private contractor. And I've been interested in Mathematica for some time. I initially had my experience in the 1990s and then got interested in March of this year. We've been talking about interfacing Mathematica with real-world sensors, and I've been interested in the Wolfram devices. But more than that, we're kind of interested in doing an artistic interpretation of the data as it comes in, not a precise usage that fits within certain bounds, but things that will modify exponents on surfaces or coefficients or various other parameters, their rotation. But I'll get into it in more detail as soon as he is finished.
Absolute horror. 50 Cent.
Raw dope in this case is program code.
Absolute horror. Absolute horror. We're going rapping. So there are these things where you have to be careful as you knit new knowledge in.
Okay, so that was a little demo.
Okay. Cool.
And now we'll switch it back, and Tom will talk about his part in the code.
Okay.
And that's the end of my part.
Okay, we're interested in connecting Mathematica visualizations to external data for art and for study. Okay, can everybody hear me? Okay, very good. And here's the beginning of the slideshow. And what you can do to intercept real data and display it is to use a simple manipulate. And right here you see something that I'm not sure that I can display full screen, but oh boy.
Anybody would like the ray glasses? There's only two you can share them. You can share them around. So I can pass it back to somebody when they
Okay, if you'll give me a second, I have something running in the background and this thing
And we like to load up all different types, like I was saying,
Okay.
going through the mathematical landscape,
Yeah.
CAs, and a lot of stuff like that. We just
Yeah, well, please. Yeah, okay. Here's a manipulate, and depending upon the whims of your clicking and dragging, you can change how various parameters on this function are affected. And what we would really like to do is to take the data from the real world and to perhaps in this particular application, we're using MIDI data, and we're generating it from a synthesizer, and we're taking it into Mathematica. And basically, we have to have a connection between the MIDI data and the Mathematica program, and what I use is J-Link. And I actually have a Java program that connects to the USB and pulls in this data and massages the data and then presents it in public variables to Mathematica. And when I run the visualization in Mathematica, I can move my finger on the K oscillator, the synthesizer here, and show the results. So the process that I use is simply to connect the synthesizer to the computer's USB port, and then I write a Java program to read that port and prepare the incoming data stream for Mathematica. And if any of you know Java, there is a very nice MIDI package that can connect to various ports and receive live data and manipulate that data into various forms. That's what I use in Java. The JavaX sound MIDI package. I normalize that data that I get in so that I can use it within the bounds of 0 to 100 on a 2D slider in Mathematica, but I do this in Java because the interpreted nature of Mathematica would slow down the visualization and produce a lot of lag if I did it within Mathematica. So I hand off that normalization and data formatting job to Java. And I embed the Java program into Mathematica via JLink. So, yeah, that's basically what I do. And within the Mathematica source code, I have various variables that are named the same as those in the Java program, and I basically access the object returned from the Java program and place those variables into like-named variables in Mathematica. And I make the variables in Mathematica dynamic so that they update wherever they are used within the notebook. To give you an idea of how the Java code looks, I've highlighted here, and you can look at this notebook at your leisure, my comments on, for instance, loading in the Java sound MIDI file and how I use it and how I loop through and look for the various devices that are connected, and how I assign various parameters from the MIDI stream to variables in Java, and I declare them public in the class so that they be accessible through JLink. The Mathematica code is kind of interesting. Right here at the very top, I specify that I need JLink, and then I specify a long path. You can see where I have the Java classes, and that basically exposes the API of my program to Mathematica, to this particular notebook. All of these variables here are local variables to the notebook, but later on, you see I have them set up as dynamics in the code so that they can be used in my various plots. Later on, like right down here, I actually read in the data from the Java object and assign it to the Mathematica variable, which is made dynamic, so it changes throughout the application. There are a lot of little details to what I did here to make it work for various devices here, but I won't get into them now. This right here is a function that basically operates differently depending upon what button you press on the synthesizer. You can display 5 or 6 different functions. What I hope to do is to have each of these buttons display a class of functions, like linear polynomial functions, trigonometric functions for one, various classes of cellular automata, and then you would turn a dial on the synthesizer, and you would get various instances, various kinds of functions, like maybe 100 for each. And there are a few things that I would like to do besides that to improve this application. Like what I just mentioned up above, the first bullet, the dials on the synthesizer could also rotate a plot. And there also is, depending upon the function that I'm using, you notice the cellular automata in our demo flicked by very rapidly, but the hyperbolic paraboloid with trig functions had a little bit of a delay. Well, that could be solved by means of taking several still shots of the particular plot for where you want, where your range is, on the touchpad on the synthesizer, and then interpolating between those stills. And you can use something called B-spline to do that, or B-spline graphical. And I hope to be building that in soon. The last bulleted area is something that I'm aggressively working on, and that is to take real live signals, noisy signals from a speaker or a microphone, and decomposing them using a Fourier analysis or a wavelet analysis, possibly first with a fast Fourier analysis. And then we could have plots and in different objects moving in accordance with changes in melody and changes in rhythm. And that would be very exciting, because we could use that kind of analysis to manipulate and provide feedback for, let's say, a microscopic image of a paramecium moving across a field of vision, for instance, affecting background tessellations and fractals or whatever, as it moves. And the patterns that result from this natural feedback might be very interesting in themselves, not just for entertainment purposes. So let's see, do I have anything else? That is basically what I want to cover. Does anybody have any questions about the programming involved? Go ahead.
And like Tom said, you can load the different types, like you can load CAs and stuff by pressing the buttons on the top. And like, for example, you have 8 slots. We were looking at in like the geometrization conjecture, there's 8 kinds of 3 manifolds. So you could load them on the 8 buttons, and then by turning knobs, you could transform those manifolds and use some differential geometry and stuff. That's the type of thing that we're looking at. We've only been doing this for a couple months, so like in about a year or two, this is going to be a lot bigger system. Since it's getting late, we could show you another time or something more like, is this moving here? Okay, as you see it moving, why don't I just show you one last thing to make it funky? Hello? 1 1 1 1 1 1. Okay, then let's turn it up. Okay. So if you one. Change it. Here we go. Turn it down a little. Get the right volume. Okay, thank you. That's the end.